All right, we're going to reflect on motion graphing. This is a continuation from the previous e-learning assignment from Friday. Right here says, describe different types of motion that are represented by distance time graphs and velocity time graphs. Listen to the video and make a race summary. So this is the video, and we're going to listen to it right now.
Hey everyone, so I just want to kind of go through my thought process in solving some of these problems, just to maybe see if kind of talking through my reasoning will help you in terms of understanding one way of solving these problems or looking at these, right? So kind of looking at our top left image here, we're given a position versus time graph since it has the x here, and we need to draw the corresponding velocity versus time and acceleration versus time. So our position versus time graph, we see here that whatever our object is, it has a constant slope, which basically analyzing means that our change in position is going to be the same amount for every unit of time, right? So basically another way of thinking of that is our displacement is the same. And we're getting our position's getting bigger and bigger at a constant rate. So that means our velocity is going to be positive, meaning our displacement value is going to get larger and larger, and it has a constant value, right? It's the same displacement every time. So we have, wow, it's really hard to draw a straight line with this thing. Anyway, so that's supposed to be a straight flat line here with some constant positive value. Right? And since our velocity is constant, that means we have no acceleration. Since accelerations are a change of velocity over time, our velocity doesn't change. So our acceleration value here is 0. We can do a similar analysis here with this position versus time graph. We have a negative change in position at a constant rate. So our velocity is going to be a constant negative value. And what that value is, we don't know. But we know our value for position is getting, in a sense, more and more negative. It's headed towards the negative direction. So our velocity is going to be negative. Right? Our change in displacement is negative. Another thing to just look at is we have a constant negative slope. So we have a constant negative velocity, since the slope of a position versus time graph is velocity. Right? And again, we have a constant value for velocity, so our acceleration is, again, 0. Analyzing one of these position versus time graphs, we see here we have curves. In this class, the only curve we're going to have is going to be in part of a parabola, or a whole parabola, depending on the problem. But it's going to be parabolic in nature. That basically means that all the problems we'll be dealing with have constant acceleration. Whether that be 0, if we don't have a parabola going on, like these two guys, or a constant acceleration of some value. So looking at our position versus time graph here, we have first initial some position at 0, and that value is getting more and more positive. Right? So that means our velocity initially, well, let's see, we have a very, very small velocity, very, very small change in position here. So velocity is going to start off at 0, but then our position gets bigger and bigger and bigger over time. So our displacement's getting larger and larger over time. So that tells us our velocity starts at 0, and then it goes bigger and bigger. And this is going to be at a straight line. And since our velocity is increasing at a constant rate, this means we have a constant positive acceleration. Kind of similar analysis here. Here, again, we start with a very small change in position over time. So very small velocities, meaning small velocity, I mean to say small speed. So our velocity, again, is going to start at 0 because we have a small displacement. And then it gets bigger and bigger. But it gets bigger and bigger in our negative direction. So velocity is going to start at 0 and then get more and more negative at a constant rate. So then looking at this here, we can look at slope here. We have a constant negative slope, so acceleration. So that's supposed to be a straight line again. Flat line this time. Another way of looking at it is our velocity is getting more and more negative over time, and it's doing so at a constant rate. So acceleration is going to be a constant negative value. So that kind of gives you the one way to kind of look at these problems. These problems here are not any different. We're just analyzing them piecewise. So we draw our situation for this side on the left side of their dotted line, and for this side on the right-hand side, so we just use a similar analysis. But I just kind of want to maybe go over one of these that we start with velocity versus time graph. Right? So if we're looking at this left guy here, we have a constant positive velocity. Well, we know that our change in position is going to be the same amount for each unit of time from this, and we know our velocity is positive, so our change in position is going to be more and more positive. I'm going to assume we're going to start at 0. We don't have to make that assumption. You could, for example, start here and draw your line up this way. But if we happen to start at a location of 0, that's what our position versus time graph looks like if I were able to draw a straight line. Since our velocity is constant and acceleration is our change in velocity over time, we don't have a change in velocity, so our acceleration is 0. Now we have a slope to our velocity versus time graph. Here we have a value where our velocity is increasing at a constant rate. So our position versus time graph is going to have a slope. It's going to be some sort of parabolic shape or part of a parabola. Again, I'll assume we start at 0 here, perhaps. I guess it depends on a problem here. But we have a constant positive velocity. So that means if we, let's say, started at some position, our position is going to be increasing over time. And the amount that it increases is going to get bigger and bigger every time, right? If this here was a value of, let's say, 5 meters per second, up here it's going to be 10 meters per second. So our value is going to get bigger and bigger over time, in positive direction. So if we started at 0, we'll have this part of a parabola or so. Our acceleration versus time here is we have a constant positive slope. That's one quick way of looking at it. Another way to think about it is our velocity is increasing in the positive direction at a constant rate, so acceleration is positive. Looking at this third situation here, we have velocity initially at 0, right? And then it's going to get more and more negative at a constant rate. Right? So we know our position, our position is going to get further and further away. It's going to get bigger and bigger, but in the negative direction this time. Right? So let's see if we draw something like this. Right? We've got initially, let's see, our displacement is very, very small, right? Which is around 0, but our displacement is in the negative direction. And over time, right, our displacement gets bigger and bigger, which means our velocity gets, our speed gets bigger and bigger, but in the negative direction since our displacement is headed towards 0. So that's what we've got here. For acceleration, right, we've got a velocity that starts near 0 and gets more and more negative at a constant rate. That's going to be a negative constant acceleration. Right, so hopefully that was helpful kind of seeing my thought process in solving some of these problems. So please look at this and let me know if you guys have any questions. Hey everyone, so I just want to kind of go through.
Okay, so you're going to do a race video over this, and then on the next slide here, we're going to talk about net force notes, and you're going to use this space to jot down notes and drawings that'll help you remember important ideas about net force, and we're going to watch a video based on net force for you to do a race video on as well.
What's up? It's Likeable Science, and today's topic is force and net force. You use force every day when you push or pull. You even used force to click on this video. And so, for all you Star Wars fans out there, as BB-8 says it best, may the force be with you. So what is force? Apparently it's strength and energy is an attribute to physical action, or okay, in simple terms, it's when you push or pull an object. Every time you push or pull an object or use force, you're also releasing energy, and that energy is released in newtons. If a person is pushing a car, they're putting force on the car and releasing energy. This could be said as John uses a force of 8 newtons, or 8N, to push the car. Let's use this as an example. One person could be pulling a rope using a force of 5 newtons, but what happens if another person pulls the rope? If more than one force is acting on an object, they can actually be added up. This total amount of force is called the net force of an object. To find the net force, we either need to add or subtract the two forces. When two people pull or push in opposite directions, you subtract the two forces. But when they pull or push in the same direction, then you add the forces. Steve is using 5 newtons of force, and John is using 10 newtons of force. Steve and John are pulling in opposite directions, so we have to subtract. There's no such thing as negative newtons, so our setup can't be 5 newtons minus 10 newtons. It has to be the other way around to get a positive answer. So it would be the net force equals the bigger force minus the smaller force. John uses 10 newtons and Steve uses 5 newtons, so our setup would be 10 newtons minus 5 newtons equals the net force. Calculating net force is just like regular math. 10 minus 5 is 5, so the net force is 5 newtons. So how about if the two forces were in the same direction? If Steve pushes a box using 5 newtons and John pushes using 10 newtons in the same direction, then you would add 5 newtons plus 10 newtons equals the net force. 5 plus 10 is 15, so the net force is 15 newtons. And that is net force. Make sure you like, comment, and subscribe. And besides,
All right, so that's net force. You're going to do a race video over and tell me what you learned. And here what you're going to do is you're going to tell me what is the total amount of net force that you have here. You're going to tell me how much you start off with and how much you have altogether. Same for here. How much are you starting off with and how much is it altogether? Is it balanced or unbalanced? Same here. Is this balanced or unbalanced? You're going to add these together. In this slide, you're going to take in, because it's going in opposite directions, you're going to subtract this number from this number and tell me, is this an unbalanced force or a balanced force, and how many newtons are being used? For this right here, you're going to tell me, is this a balanced force or unbalanced force? And then first you're going to add the total of the arrows going in the same direction. So you're going to add 20 plus 5. And then you're going to subtract the 10 from 20 plus 5 minus 10. And you're going to tell me how many newtons you have of force going. Right here, your arrows are moving in the opposite direction, so you have to subtract. So since they're going in opposite directions, you're going to say 20 minus 20 gives you what? Is this a balanced force or unbalanced force? You're going to calculate the net force acting on each object below. Be sure to indicate the direction in which the box is moving. So you're going to tell me, is this moving, what direction the boxes are moving, and what the net force is, and how many newtons of force there is. You're going to put your information right here. So for example, you've had this one done for you already. See if I can fix this for you. No. So you have 25 newtons minus 18. So let's see, you have 25 minus 18 right here. And you're going to tell me how much it is. Okay? So you're going to take and you're going to put your total into this box right here. So you'll type your problem here and you'll type your answer in here. Pretend you can explain net force to someone much younger than you, like a little elementary, kindergarten, first grade person. Okay? And explain how to calculate net force and how net force determines the object's motion. Right here is another race summary that you'll be doing. You're going to listen to this video and provide me with a race summary.
Did you know that physics is about how things move and why things move? It was Isaac Newton who discovered the three laws of motion. He was a scientist who lived from 1642 to 1727. Let's first learn about the first law of motion. It is also called the law of inertia. It states objects will remain at rest or in uniform motion in a straight line unless acted upon by an external unbalanced force. To understand Newton's first law completely, we need to learn about inertia first. See, this is a very large sofa. What's special about it? It's stable. It is not moving. Now go ahead and try to move it. Oh, you can't. It's not willing to move. You can't move it as it is very large. Now try to move this small stone. Good. You can move it a little bit, but you had to put in a lot of effort. It was also like it didn't want to move from its original position. Even the smaller things don't want to change their positions. They don't want to move. Even a small stone takes some effort to move. This is the first rule of physics. Things like to stay where they are. No object in this universe would start moving unless some external effort is put on it. It's like all things in the world are lazy. Now, the question is, if things are lazy and they don't want to move, then how does the movement happen? The answer is that there are so many things in the universe which push and pull other things and force them to shift their positions, like you forced the small stone to move. But as we said earlier, that things are lazy. They would try and stop their movement as soon as the effort was removed. Well, you'll be wrong if you think like that. You'd find it very strange to accept that when a small stone was still, it wanted to stay still. And once you'd put it in motion after putting some effort, it would like to keep on moving. In reality, it would keep on moving forever and ever. But somehow it stops. But it stops not because it wants to stop. It stops moving because things in its path force it to stop. It may be due to air, or if it bumps into a tree or rough surface on the ground. But suppose there were no tree in its way, or there was no roughness on the surface, and also imagine that it does not have poles or trees in its way. The stone would never stop. It would keep on moving. It happens in outer space, where there's no air or roughness. If you kick a small stone, it'd keep on moving and moving and would never stop. So how can we say that things are lazy? See, the small stone wanted to move forever, but it was stopped by the resistance of air, trees, or roughness of surface. It's like you moving on a slippery road. You'd keep on moving unless there was some effort put in to stop you. The same is true with the small stone in outer space. It would keep moving, as nothing came in its way. It also doesn't want to stop, as it is too lazy to do that. So now we can change the first rule of physics. Things want to stay in the position they are, to things want to keep doing what they are already doing. If things are at rest, they want to stay at rest. And if things are moving, they want to keep moving. In other words, things are lazy. So there's a lot of laziness in the universe. Physicists have a special name for this laziness. It is known as inertia. So now you understand Newton's first law of motion. Can you write it? Well, you are very much right. Now let's move on to Newton's second law. As we know from the first law that to overcome the inertia of an object, we have to apply unbalanced force. Newton's second law talks about how fast an object would move. Well, it states acceleration of an object depends on the mass of the object and the amount of force applied. In mathematical terms, Newton's second law states that force is the product of mass and acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. Look at these two swings. If you apply the same force on both swings, check whose goes faster. Let's first push the little kid. See? It goes very high. Now push this fat man with the same force. See, it does not go far, because it has more mass than the little kid. So the more mass there is, the force required to push the object is also greater. Let's look at the mathematical formula of the second law again. It's the product of mass and acceleration. We've already learned that if there's more mass in an object, to move it, we need more force. Now let's see this kid sitting in the swing. If we apply little force, then it goes a small distance. Now if we apply a lot more force, it goes very high. So to get more acceleration, we need to apply higher force. So now you can understand the relation among force, mass, and acceleration. Until now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Ah, Well, it moves according to Newton's third law, which says that for every action, there is an equal and opposite reaction. To understand this, see what happens when you drop a tennis ball. As the tennis ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it backwards? Huh? Oh, nothing happens to it, since the earth is very big as compared to your bicycle. The force applied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
Hey guys, what's up? So I am super into this website right now. It's
Okay.
Generation Genius. And they cover
Okay, so that's Newton's laws of motion. You're going to take and do a race format and tell me about the three laws. Here on slide 10, you're going to think about these terms: balanced force, unbalanced force, and net force. I want you to think about how to demonstrate these concepts. You can use prompts in your room, or a whiteboard to explain your type of force, or you can draw it over here. You can insert pictures of yourself or make a video clip and insert it here as well. So you need to demonstrate balanced force, unbalanced force, and net force, and take pictures or draw pictures and insert them here. All right. Read the definition and choose the term that best matches. Click and drag away the term to reveal if you are correct. So if it's a push or a pull, would that be force or net force? Let's say that it is force. You're going to take and you're going to drag it away over here, and you'll see that it's correct. If it's incorrect, then cover it back up and pick the right answer. And you'll continue to do that all the way through. Look at the terms on the left and match them to the example on the right by inserting an arrow to the term or the example. Or you could just simply put A, B, C, D, E, F on by the number here if you choose to do that instead. For instance, what is friction? Is it 65 miles an hour north, 10 miles per hour, rubbing hands together to warm them, turning a corner but not speeding up, pushing a bike up a hill? What is speed? 65 miles per hour, 10 miles an hour, rubbing hands together to warm them, turning a corner but not speeding up, pushing a bike up a hill. What is velocity? Is it 65 miles per hour north, 10 miles per hour, rubbing hands together to warm them, turning a corner but not speeding up, or pushing a bike uphill? What is acceleration? Is that 65 miles per hour, 10 miles per hour, rubbing hands together to warm them, turning a corner by not speeding up, or pushing a bike up a hill? What is applied force? Would that be 65 miles an hour, 10 miles an hour, rubbing hands together to warm them, turning a corner but not speeding up, pushing a bike up a hill? Right here, you're going to tell me who Sir Isaac Newton is and what each of his laws are. I know it says to just fill out one, but there were several on this particular presentation, so I eliminated it and made it just one. You're going to take and you're going to tell me who he is and what each of his laws are called and what they represent. Right here, you're going to take and you're going to determine which one is inertia, which one is friction. Then you're going to give me 3 examples of inertia right down here. And that is all for today.